All right, so we're going to continue looking at section 3.1. The first thing I just put up here is just a reminder of when you do your inverse sine, inverse cosine, inverse tangent, what you get an answer between. All right? So if you remember the sine function, it looked, just to give you an idea, something like this. And it continues in each direction. We decided that if you only focus on the section from negative 90 to 90 and forget everything else, in that section you will only get one answer for every problem. Okay? If you don't look at that section, you won't get one answer. We did the same idea for cosine. We focus on the section from 0 to 180. That way when we do inverse cosine, you only get one answer. And inverse tangent is also negative 90 to 90. But what's the difference between the negative 90 to 90 on the sine and on the tangent? I didn't write it this time, but I did yesterday. Yeah.
It can't be exactly negative 90 or... Oh, it can't be exactly negative 90 or 90?
In the
tangent?
In the tangent one. So when we do inverse tangent, you'll never equal 90. And if you look at your chart, it says undefined at 90. Okay, it's just a reminder from yesterday. And I did that because you're going to see those numbers pop up again today. All right, so the first thing we're going to look at is when does inverse sine and regular sine, when do they cancel out? Okay. So I told you that inverse sine, regular sine, or any trig function and its inverse, they're opposites, and they cancel each other out if you put them right next to each other. But that only happens for certain values of x. And when it happens for this one, is any value between negative 90 and 90. And that has to do with what we looked at yesterday. I'm not going to do this for all of them, but for this one, I'll show you an example. All right, so I'm going to type in, and I'm going to do it in degrees. So I'll pick a number between negative 90 and 90. Second, inverse sine of sine. And someone give me a number between negative 90 and 90. How much? 83? All right, 83. Any reason why you picked 83? Okay. All right. So, because he gave me a number between negative 90 and 90, the inverse sine and the regular sine should cancel out. And when I hit enter, what number should I get? 83, and I do. I get back what I started with. So the answer is whatever you plug in. All right? And you could try, again, you could try any number you want between negative 90 and positive 90. All right, so let me try 15. And you get back 15. Now, let me pick a number that is not between negative 90 and 90, like 106. Okay, am I going to get back 106 this time? No. Okay, I get an answer, but I get back something different. And there's a connection between the answer I typed in and the answer I got back, but we're not really going to look at that right now. Okay. So inverse sine and regular sine cancel out as long as you pick a number between negative 90 and 90. Or if you put your calculator into radians, you could pick a decimal between, that's about negative 1.57 to positive 1.57. That's pi divided by 2. Okay, and in your book, they call that formula 2a. You don't have to know that it's formula 2a. That's just what they call it. Now, what's the difference between formula 2a and 2b? They pretty much look the same. But there is a difference, right?
The inverse of sine is inside the first parentheses.
Yep, the inverse is now inside, okay? And the regular sine is on the outside. So it's like we've switched the order of the two functions. All right, so now you have to pick a value for x between -1 and +1. Okay, and that -1 and +1 has something to do with this graph. This is the graph of sine I showed you yesterday. If you look at it, anybody tell how high that graph goes? Goes as high as 1. And about how low does it go? 3? Yeah, it goes right to -1. So the fact that this graph stays between 1 and -1 has to do with why those numbers are what they are. Okay, we'll study more of the graphs next week. Okay, so let's try one of these. So let's try sine of inverse sine, and we'll pick a number between -1 and 1, 0.76. Okay, so Mason, when I hit enter, what should I get?
0.76.
Yeah, I get 0.76. So the answer that I get is whatever I typed in. All right. Orion, give me a number that's not between -1 and 1.
Not between -1 and 1?
Yeah, anything.
2.
2. All right, so type in 2. This time, when I hit enter, I don't even get a different answer back. I just don't even get an answer, okay? So we have to stay between -1 and 1. And again, the reason I can kind of tie it in with a graph, just to see why. Okay, what number did you give me? 2, right?
Yeah.
Okay, you gave me 2. Where does that red line and where does that blue curve cross? They don't. All right? By typing in that question right there, you're asking where do the blue line and the red line cross, if you want to think of it as a picture. And you guys just said they don't. That's why I got an error. Okay? So if that kind of helps, that's the reason why. So the kind of questions you'll see on these, it could be written one of 2 ways. This is a yes-no kind of question. So it says, is the inverse sine of the sine of pi over 8, is that equal to pi over 8? Would you get back what you started with if you typed that in? Bless you. Okay, Peter, is this formula more like 2a, or is that one more like 2b?
I guess, maybe you're talking about the example one?
Yep, example 1.
I guess more like 2A, or 2B, sorry.
All right, why do you say 2b?
Because that's the, I don't know. I haven't been paying attention.
What's the difference between 2a and 2b?
Are there like different steps in some, or are they two completely different? Because one of them has the inverse function on the outside, and one of them has on the inside.
Okay, so that's the difference. So using what you just said, if you look at example 1, what pattern does example 1 follow?
Canceling out the inverse and that inverse function.
The inverse is where?
Outside.
Outside. So is that 2a or 2b?
2.
2a. Okay, so inverse is on the outside, regular is on the inside. So here is what you're looking for, between -pi over 2 and +pi over 2. Okay, so think of that on like a number line. Anywhere in here is good. All right, so Eric, we're looking at pi over 8. How does pi over 8 compare to pi over 2?
It's smaller.
It's smaller, right? If you take 3.14 and divide it by 8, it's smaller than dividing by 2. But it's still, is it still a positive number? Yeah. So if 0 is right in the middle, pi over 8 might be right there. Smaller than pi over 2, but it's still a positive. So it's somewhere in the area that it's okay to be. So would that work if I type that in? Yeah, that would be fine. So the answer to that question is yes. If you type that in, yeah, it would work. All right, let's look at this one. Paige, what formula is this one like? 2a or 2b?
2B.
2b? How come?
2A, because the inverse is on the outside.
Yes, 2a because the inverse is on the outside. So now we're using the same restriction we used last time. So Molly, the number we're working with is 3 pi over 2. How does 3 pi over 2 compare to pi over 2? It's bigger, right? It's 3 times as big. It's pi over 2 tripled. If it's bigger, is it going to be somewhere in there? No. So since it's bigger, no, that would not work. If you want to think of that in degrees, 3 pi over 2 is 270 degrees. It's not between negative 90 and 90. Okay, so that one doesn't work. Let's look at this one. Okay. Connor, which formula is that one like? 2a or 2b?
2b.
Yeah, 2b, because we get the inverse on the inside. What do I have to be between for 2b?
Negative 1 and 1.
Am I between negative 1 and 1?
No.
No. So that one wouldn't work. If you type it in, you would get an error. Okay, that wouldn't work. All right, let's try one more. The sine of the inverse sine of 0.6. Okay, so Robin, 2a or 2b?
2B.
Yep, 2b. So Connor just told us we got to be between negative 1 and 1. Am I between negative 1 and 1?
Yes.
Yes. That would work. Okay, so any question on that one? Okay, the only other way you could see a question like this asked a little differently is the directions could say simplify the sine of the inverse sine of 0.6. If you get a question that says simplify, don't write yes. Okay, yes doesn't tell me much. It's not a yes or no question. What would the answer to this one be? 0.6. Yes. Okay, so if it's a simplify, it's going to be a problem that you can do. It's not going to be an error or something like that. But just don't write yes. That doesn't answer it. Okay, any questions if I ask it that way? All right. Okay, so those are your formulas for inverse sine and regular sine. Now we'll look at the same thing with cosine, and then we'll look at it with tangent. Anyone remember from yesterday, what did we have to be between for inverse cosine? 0 and 180? That's exactly the same thing here. Okay, so inverse is on the outside, regular is on the inside. You could be between 0 and 180. Okay, formula 4b. Again, you don't have to know that. I'm just referencing the one in the book. But that's formula 4b. The inverse is on the inside, regular is on the outside. Now, we didn't look at it quite as closely, but does anybody remember the graph of cosine and how high and low that it went? Rudy? 1 was the highest? And what was the lowest? Do you remember? Anyone remember what the lowest was? Not negative 2, it's symmetrical, so it's 1 and negative 1. All right, so it's the same. The only difference between sine and cosine, if you graph them at the same time, is it looks like one of them has been kind of shifted left or right. Right, so if you took the red graph and shifted it to the right a little bit, or took the blue one and shifted it left, they would be identical. Right, but they have the same height, 1 and -1, and that's where that restriction comes from. Okay, so we won't go through as many as we did for sine, but we'll try a couple. Okay, the cosine of inverse cosine. Alex, is that one more like formula 2a or 2b?
2b, because the inverse cosine is on in the parentheses.
Yep, perfect.
4b, sorry.
Inverse is on the inside. And what do you have to be between for that formula?
-1 and 1.
Are we here?
Yes.
Yes. So that's it. That's the answer to that one, yes. Okay, let's try inverse cosine of 210. Would that equal 210? So Emily, is that one more like 4a or 4b?
4A.
Yeah, that's 4a because the inverse is on the outside. What do we have to be between for 4a?
0,
Okay, are we between 0 and 180? No. So that would not work. Would you get an answer back if you typed that in? What do you think? Would you get an answer? Yep. Connor? Yeah, you'd get an answer. It just wouldn't be 210. The ones where you wouldn't get an answer is like the one above it. If you put in 1.95, that's where you're trying to find where that line and the wave cross, and they don't. Okay? Hey, so any questions on that? Okay, so there's your inverse cosine. And now let's look at inverse tangent and regular tangent. Zach, do you remember from yesterday what we had to be between for angles?
-90 and 90.
And could you include -90 and 90? Not for inverse tangent. So same restriction as yesterday. Now, the B formula, okay, 2A, 4A, or I'm sorry, 2B, 4B, 6B. That restriction always comes from how high and low the graph goes. Well, I never showed you the graph of tangent. So let's take a look at it. And let's see if we can figure out how high and low the graph goes. So I'm going to get rid of sine and cosine. Type in tangent. And that's the graph of tangent. So there's a pattern to it, but it's not a wave anymore. How high and low does it look like that graph is going? How high? Really high. How high is really high? Right?
Infinite.
Infinitely high. And how about how low?
Infinite.
Infinite. If you're thinking, well, maybe it just stops at the edge of the screen, I can zoom out. Everything's going to look smaller. That's interesting. It doesn't stop. Let's. So it looks like it. When I zoomed out, it almost looked like it just stopped at 4. Let me just set one number a little higher instead of everything. Let's make that 8. Okay, so you can see it's going up, but the problem is it's getting so steep that the calculator can't draw it. Okay, the calculator can't really draw vertical lines on the screen. So eventually, it's just so steep that it can't even draw it. All right, that's sometimes a problem with a calculator. If you depend on it too much, you don't get an accurate picture. Okay. But it's exactly as Ryan said. It goes up forever and down forever. So this formula always works. It always works. So if you get something with inverse tangent on the inside, you shouldn't even think about is it true or is it false. It's true. It's always true. Let's try that one. So Emily, if I did the tangent of the inverse tangent of 30.4, would I get 30.4?
Yes.
Yeah. Inverse is on the inside. That's the one that works all the time. Okay? The answer is yes. And that's the only one I was going to do for inverse and regular tangent. Okay. Any questions on that? Okay, so that finishes up what we had left in section 3.1. Okay, so the last section, we'll do half of it today and half of it tomorrow, is right triangle trig. How many people remember like SOHCAHTOA, like from geometry, stuff like that? People remember? Okay. If you remember that, that's kind of what we're doing here. But we're going to combine that idea with inverse trig. And maybe you may or may not have done that in geometry. All right. So first of all, just some basic definitions about the kind of shapes we're going to work with in this section. Hayden, what's a right triangle?
Triangle with 190 radius.
Yeah, it's a triangle with a 90-degree angle. Okay, now in the triangle, we've got three sides, and we have names for all the sides. Alex, do you remember the name of the two short sides in a right triangle? How about the long side? Yep, the long side is the hypotenuse. Anyone remember the names of the short sides, Rudy? The legs. Okay, and the symbol for a 90-degree angle, just as a reminder, is that little thing in the corner there. It kind of looks like it makes a square. Okay. And in that triangle, we're going to be dealing with, bless you, we're going to be dealing with the acute angles. We're not going to be dealing with the right angle. The right angle is always a 90. Anyone remind me what's an acute angle? And this triangle has two of them. Yeah?
Smaller than 90 degrees.
Smaller than 90. Does it have to be anything else? Yeah? I can think of an angle that's smaller than 90 that's not acute. In fact, there's infinitely many of them. So your angle has to be what kind of number? It has to be positive. Okay, we've talked about negative angles, like negative 10 degrees. Negative 10 is not acute, even though it's less than 90, but it's got to be greater than 0. Okay, Pythagorean theorem. What kind of triangle do you have to use that theorem? Because you can't use that theorem on just any triangle. And anybody know what kind of triangle you can use it on? Right?
Isosceles.
It could be isosceles. We got to use a little different classification. It is possible it's an isosceles, but this wouldn't work on any isosceles. It wouldn't work on this one, assuming those are equal. Paige? It has to be a right triangle. Okay, so to use Pythagorean theorem, you have to have a right angle. If you tweak the Pythagorean theorem a little bit, then you can actually use it on anything, not just right angles. We'll look at that in 2 weeks. Okay, but for now, we're just going to stick with right triangles. And does the Pythagorean theorem have something to do with the angles in the triangle, or something to do with the sides? Yeah. It has to do with the sides. Do you know what it says? Can you tell me what it is? What's A, B, and C?
We have two short sides. It's the hypotenuse.
Exactly. So the idea of the Pythagorean theorem, whatever you want to call the sides, usually it's A, B, and C. But what Alex just said, you take the short side, square it, plus the other short side, square it, and that's equal to the long side, squared. That's the Pythagorean theorem. A squared plus b squared equals c squared is not the Pythagorean theorem. That's how people usually express it, assuming that A is a leg, B is a leg, and C is a hypotenuse. Okay. If you want to really explain what it is, it's leg squared plus leg squared equals hypotenuse squared. Hey, any questions on that? All right, so before I can go through and define the 6 trig functions like SOHCAHTOA, if you're familiar with that, the definitions are going to use a couple words that I need to make sure we're clear on. The words opposite and adjacent. Okay, the words opposite and adjacent are kind of like the terms left and right. Okay? If I tell you to go left, what does that depend on? If I just say go left. Yeah?
Your point of reference.
Yeah, it depends which way you're facing. Okay, for me, left is different than for you because we're facing different ways. But now if I said, for example, go north, is that the same for everybody regardless of which way we're facing? Yeah, because north is it's a point of reference that's not relative to you, it's relative to Earth. So opposite and adjacent are more like the terms left and right. They're relative terms, okay, depending on which way you're facing. So opposite is the side that's farthest away. So if that's your point of reference, that side is opposite. It's the one that if you were standing in that corner and you looked out, what side would you see? And adjacent is the side that's right next to it. Okay, now you can take the same triangle, make a copy of it, change your point of reference, now go stand at the other angle, and now everything switches. Opposite is the side that's furthest away. Adjacent is the side that's right next to your angle. Now, there's 2 sides, technically, that are right next to your angle, but what is the long side always called? That's always the, how about Mason? That's always the hypotenuse. Okay, the hypotenuse is kind of like saying, go north. Doesn't matter where you stand. The hypotenuse is always the hypotenuse. That never changes. But opposite and adjacent do. Okay, any questions on that? Okay. So, opposite is the side in the triangle. Another way to think about it, if thinking of it as the furthest away is kind of confusing, it's the side that has nothing to do with the angle being referenced. Okay, so if you had a triangle, try to draw this as 3 separate pieces, hopefully. Yep. Okay, so opposite is the side that if you took it away, you still have an angle there. The side that I just took away has nothing to do with the angle that I'm talking about. But adjacent, if you took that side away, well, or if I just erase it, Now you don't have an angle anymore. Okay, you just lost one side of your angle. So adjacent is the side that if you took that away, because it's right next to your angle, you don't even have an angle anymore. So adjacent is the side that's directly next to one of your angles, but it's not the hypotenuse. That's also next to your angle. So again, I explained that those are relative terms, like left and right. Depends on your point of reference. Okay, so any questions on the terms opposite and adjacent, or why they are relative terms? Okay, so now that we know, or hopefully know what opposite and adjacent mean, now I can give you the 6 definitions of our trig functions. So we've defined these before as y over x, things like that. Okay. That's defining it on the unit circle using a coordinate. Okay. What we're doing here is referencing sides in a triangle. Let's just worry about the 3 on the left. So sine is the opposite side divided by the hypotenuse. Cosine is the adjacent side divided by the hypotenuse. And tangent is opposite over adjacent. All right, now if you look at that, I'm going to compare it to what we just did last week with y over x. Okay, so we had unit circle. Let me make it a little bigger. So there's our unit circle. We may have a point on it somewhere. We draw our triangle. That's x, and that's y. And that is just the hypotenuse. Does anybody remember what we said sine was equal to last week? What letter was sine? Yeah,
Y.
sine was y. Do you remember cosine?
X.
X. And how about tangent?
Y over X.
Y over x. That's what we did last week. Okay, well, let's look at this. What side is y relative to that angle? Yeah,
Opposite.
opposite. And how about x?
Adjacent.
X is adjacent. Very good. Y is opposite, x is adjacent. Look, if you use the idea we did last week and what we're doing this week. Sine is opposite over hypotenuse. Right? Well, sine was y. What was the hypotenuse last week? It was always what number? 1. So if you want to think of it as being over 1, which was your hypotenuse, you can. Y is opposite. 1 is the hypotenuse. Opposite over hypotenuse. Same with cosine. X is adjacent. 1 is the hypotenuse. That's adjacent over hypotenuse. Okay, tangent. Y over x. Opposite over adjacent. That's exactly what we're saying this week. So what we did last week and what we're doing this week, it's the same thing. It's just a different way of looking at it. And now, once we had the 3 on the left, what did we do to get the 3 on the right? Flip them. Okay, so just flip everything. So your cosecant is hypotenuse over opposite. Your secant is hypotenuse over adjacent. And your cotangent would be adjacent over opposite. Okay, so that idea of flipping them works exactly the same as last week. And now there's a trick that you can use to remember those three, and I kind of hinted at it earlier. Does anybody know what the trick is? It's like a word, Katie?
SOHCAHTOA.
Yeah, can you explain that, or
Um,
what's going on there?
it's just the trig functions with opposite over hypotenuse and all that.
All right, how do you spell that? What do you do?
SOH,
Yeah,
CAH,
yep.
TAOA.
TOA. So the way that might help you is sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. Okay, just reading down. Okay, anybody seen that before? SOHCAHTOA? Yeah, so that might help you. All right. One year when I asked somebody what's the trick you can use to remember that, they said Sacagawea. So she explored some stuff, but she's not going to help you with trig. So SOHCAHTOA, not Sacagawea. All right. So let's see if we can figure out the 6 trig functions of that triangle. What's missing here before we could even start this problem? You might be able to do some of these, but you're missing something you're going to need eventually. Matt? Yeah, you're missing the hypotenuse, and you're going to need that for sine. It's opposite over hypotenuse. You need it for a bunch of them. How can I get the hypotenuse here?
3 squared plus 4 squared.
Yeah, 3 squared plus 4 squared equals x squared. So what's my hypotenuse, Matt? 5. Okay, it doesn't always have to come out nice, but I just picked one to start with that came out nice. Remember all your rules. If it does come out to a square root and it ends up in the bottom of a fraction, just like last week, you need to fix it. Okay, so let's start with sine. Ashlyn, what's the definition of sine?
Sine is opposite over hypotenuse.
Okay, what's the opposite here?
The opposite would be, so it would be 4.
4. And what's the hypotenuse?
5.
5. Good. There's your sine. Okay, Ileana, what's my definition for cosine?
Adjacent over hypotenuse.
Yep, adjacent over hypotenuse. And what's my adjacent here?
3.
3. Hypotenuse? 5. Perfect. So 3/5. And Peter, my definition for tangent?
Opposite over adjacent.
And what's the opposite here?
4.
Adjacent? 3. Okay, so we got those 3. Eric, what do I do now to get the other 3?
You can just flip sine.
Yeah, just flip all of them. Right? Flip each one of them. So 5/4, 5/3, 3/4. Yeah, again, I wouldn't ask you to do all 6 in the same problem, but we're just practicing all 6. Okay. Any questions on that one? All right. Okay, next thing, the last thing we're going to look at is going to kind of combine 2 ideas. And one of the ideas is complementary angles. Does anyone remember what complementary angles are? Yeah, go ahead, Alex.
Add up to 90?
Yeah, it's two angles that add up to 90. Technically, they have to be positive angles. So you can't say, well, 100 and negative 10. Well, those add up to 90, but they're not positive. Okay, so I'm going to make a statement using complementary angles, and I'm going to say that the two acute angles in a right triangle are always complementary. Why? Why are the two acute angles in a right triangle always complementary? Katie?
Because all the angles inside of a triangle add up to 180.
Okay, so all the angles in a triangle add up to 180. But why do those have to be complementary?
Since one angle's already 90.
Right. That's the other piece. They all have to add to 180. In a right triangle, one angle's already 90, so that only leaves 90 left for the other two. So if the other two add to 90, they're complementary. All right, so let's look at this, and then I'm going to draw a picture tying these two ideas together. Okay, the idea of co-functions. Okay, so we've been kind of pairing up the functions as reciprocals. Reciprocal means you flip the one on the left to get the one on the right. Okay, sine and cosecant, cosine and secant, tangent and cotangent. Those are, bless you. Okay, those are reciprocals. Well, kind of a different way to think about trig functions, a different way to match them up is what we call co-functions. And the way cofunctions work is you pick a trig function, and then you put the word co in front of it. That's its cofunction. So I've got sine, and the cofunction of it is cosine. Just has the word co in front. We've got secant. If you put co in front of it, you get cosecant. And the last one happens to just be the same as the pairing we've been doing all along, tangent and cotangent. Okay, those are your three pairs of cofunctions. Any questions on that? Okay, so now I'm going to try to connect those two ideas. Okay, what I've drawn here is a right triangle. As generic as I could, I didn't label the hypotenuse, but because I'm not using it. But I didn't label the sides and I didn't label the angles. Generally, when we do right triangle trig, you use A, B, and C for the sides, and you use those two Greek letters for the angles. You always want to make sure that you put alpha across from A. Alpha always goes across from A. Does anyone know the name of this other Greek letter? Yep, beta always goes across from B. That's how you always set it up. All right, so let's see if we can find, we can label that C. We might use it. Let's start with that first pair, sine and cosine. Let's find the sine, and then I got to pick a point of reference, so let's do it from the perspective of alpha. Okay, Connor, what's sine again?
Opposite over hypotenuse.
Opposite over hypotenuse. What side is opposite here?
Would be
Again, from alpha.
A.
Yep, A. And what's the hypotenuse?
B. No, C.
C. So the sine of alpha is A over C. Any question on that? Paige, what's the function that we paired with sine when we were talking about cofunctions? Cosine. now I'm going to write down the cofunction. And now I'm going to use the angle that's the complement to alpha. In this diagram, what angle do you add to alpha to get 90? What angle is complementary to alpha?
Beta.
Beta. Yep. So I did two things. I picked the cofunction, and then I picked the complement of that angle. Let's find the cosine of beta. Alex, cosine is adjacent over hypotenuse. So from the perspective of beta now, what side is adjacent?
A,
A? And what's the hypotenuse?
C,
C. And what do you notice about those two things?
they're the same.
They're the same. Okay, let's try one more. Let's do the tangent one. Okay, tangent of alpha. Emily, what's the tangent of alpha?
A over B.
Yeah, it's opposite over adjacent, which would be A over B. Okay, now I'm going to find another one, but I'm going to pick the cotangent. So Emily, I just told you. What's the cofunction of tangent? Cotangent. And what angle is the complement of alpha?
Oh, beta.
Beta. It's the other angle that in the right triangle. Okay, so cotangent is adjacent over opposite. So Zach, from the perspective of beta, what side is adjacent? A. And what side is opposite from beta? B. So notice again, the tangent of alpha and the cotangent of beta came out the same. So there's a connection here between angles that are complementary and cofunctions. Okay, and it's the complementary angle theorem. Okay, that's all it is. It's what we just noticed. If you have cofunctions of complementary angles, the answer comes out the same. Okay, so we'll finish up by doing a problem with actual numbers, and I'll show you how you could use that. Okay, but cofunctions of complementary angles come out the same. So let's see if we can figure out what would be the same as the sine of 30 using its cofunction and its complement. Okay. What's the cofunction for sine? Cosine. And what's the complement of 30? 60. So the sine of 30 would come out exactly the same as the cosine of 60. Sine of 30, cosine of 60. Okay, and the reason that works is because they're cofunctions and you picked angles that are complements. Okay, let's try the next one. Tangent of 15. Matt, what function is the cofunction for tangent? Cotangent. And what's the complement of 15? Mm-hmm. 75. Okay, so those would come out the same. I'm not going to show you, but you could try it. And now Faith, I have secant. What's the cofunction for secant? Cosecant. And what's the complement of 40? 50. Okay, so those come out the same. So, where would you use that? In a problem like this. I have the sine of 15 divided by the cosine of 75. Orion, what do you notice about sine and cosine? What are they?
What is it? They do
New word we just learned today.
Yeah, trying to think of it. It's when you do the little flip thing, and then sine becomes cosine, you just have to co to it. Maybe I'm thinking of something else.
Anyone remember what's it called when you put the co in front of a trig thing? I can't tell you the thing, otherwise I'm telling you the answer.
Is it co-function?
Co-function. When you put co in front of a trig function, it's a co-function. So these are co-functions. And Mason, what do you notice about 15 and 75? They're complements. So we have co-functions of complementary angles. What does that mean about the value in the top and the value in the bottom? I don't know what they are, but I know that they're the same. Okay, there's some weird decimal. I have no idea what it is, but I know they're the same. So when you divide two things that are the same, what do you get? 1. So that's the point of that problem. It allows you to simplify in a very special situation. Okay, works with division. And it also works with subtraction. Okay, I don't know what the tangent of 12 is. Yeah, really, I have no idea. And I don't know what the cotangent of 78 is. But I do know that these two values, look at the functions, look at the angles, we can apply the theorem we just learned. Okay. What do we know about the tangent of 12 compared to cotangent 78? About Irene? Okay, the angles are complementary. How about the functions? What are those called?
They're the co-functions.
They're co-functions. And what does the theorem say if you have co-functions of angles that are complementary? They're equal. So we don't know what that is and we don't know what the other thing is, but we know they're equal. So what do you get when you subtract two things that are equal? 0. Okay, so I showed you division, I showed you subtraction. Would this idea work with addition? If you add two things that are the same, do you always get the same answer? No. You get whatever you added doubled. So that doesn't work. And how about multiplication? If you multiply two things that are the same, do you always get the same answer? No. If you multiply two things that are the same, you get that thing squared. Okay. So for problems like this, your answer usually comes out to 0 or 1, unless they did something like this. Then you have 4 plus 0, which would be 4. Okay, most of the time it's set up just like that. Okay, so any questions on that? Okay, so we looked at a few different things. We looked at those inverse trig formulas, a little bit of right triangle trig, and then complementary angle theorem. Okay, so homework on 187. Okay, those are all yes/no questions. 46 to 51, 53 to 55. And then on 255, 9 to 21, just the odds. Okay, so we'll take a look at that tomorrow, and I think we're on track to finish everything for the week tomorrow. So that means we will have a review day on Thursday.